Okay, so we finished talking about how to calculate the speed and the fact that we need to use a new gas constant in order, or at least a new value for the gas constant, in order to find the speed itself. We're going to look at a related aspect of the speed of gases, something known as Graham's law of effusion. This particular setup takes place when you have a collection of gases, or you could just have one gas actually, but here I'm going to have a collection of gases present in one receptacle. Now, in this receptacle, there's a tiny aperture, a tiny hole that allows the gases to escape. And the thing is this, if you have two different gases present in this receptacle, the two gases will escape through the hole, but the speed at which they escape through the hole will differ based on the molar weights of each one of these gases. We know that the speed of the blue gas will be given by the square root of 3RT divided by the molar weight of the blue gas. And we know that the speed of the red gas will be given by the square root of 3RT divided by the molar weight of the red gas. Okay, so here's how Graham's law of effusion takes place. Since we're comparing two gases to each other, instead of calculating the individual speeds, although that could actually be a specific problem that I ask you for, if you're comparing the two gases to each other, you could simply take the ratios of the speeds. And when you take the ratios of the speeds, you'll be taking the ratios of the square roots of 3RT molar weight 1 over the square root of 3RT molar weight 2. And since you have 3RT on both ends of the equation, the 3RTs simply cancel out. And what you end up with is finding out that V1 over V2, in other words, the ratio of the speeds, equal the square root of the inverse molar weights, right? So this is 1 over molar weight 1 over 1 over molar weight 2. So you end up bringing extremes together, bringing middles together to end up with this reciprocal end of the molar weights. This equation right here, the ratio of the speeds equaling the square root of the inverse ratio of the molar weights, is what we know as Graham's law of effusion. And the beauty of it is that you don't even need to introduce the value of the gas constant. You don't have to, in fact, change the molar weight to kilograms per mole. This can be kept as grams per mole. As long as the units of these two molar weights are the same, it doesn't matter what they are. So, the other thing though that needs to be pointed out is that, as written, what this equation is telling you is how fast gas 1 is moving in relation to gas 2. Okay? So let me show you an example. Let's say that I tell you, that you have neon gas, which has an atomic mass of 20.18 grams per mole, and you have also sulfur dioxide with a molar mass of 64.06 grams per mole. You're effusing this through a small aperture, and I want to find out how much faster neon moves in respect to SO2 out of this receptacle. Alright, so the fact that we're comparing the gases implies that we're going to be using Graham's law of effusion. Alright, so we have speed 1 over speed 2 equaling the square root of the inverse molecular weights. Alright, now V1 is the gas that you're trying to find out how much faster it's moving in respect to SO2, so you want to make V1 the speed of neon. And V2 will have to be by default the speed of SO2. Alright, now once you make that determination, neon being on top of the first fraction means that the molar weight of neon needs to be on the denominator of the next fraction. The speed of SO2 being in the denominator of the first fraction means that the molar weight of SO2 has to end up on the numerator of the opposite fraction. And notice once more that I didn't even bother changing the molar weights to kilograms per mole because we're not using the gas constant anymore. The gas constant canceled out. So you can leave this in grams per mole for both of them. Both of those units will cancel out. You'll end up with 64.06 divided by 20.18, which upon taking the square root will tell you that the value of this ratio is 1.782. Finally, solving for the speed of neon, you basically have a setup such as 1.782 times the speed of SO2, which tells you that the speed of neon is 1.782 times faster than the speed of SO2. And in essence, this is how you go about comparing the speeds of gases to each other via Graham's law of effusion. If it so happens to be the case that you do need to know what the speed of neon is, you can still use square root of 3 RT over molar weight to find it out. Alright, so I'll stop this video right there and we'll start talking on the next video about real gases.